All right, so I would suggest we get started. Suppose more people will join in the course of the talk. So welcome to the MCQST Colloquium, I think now second for this year, and it's our very great pleasure to welcome Andrea Cavalleri to our MCQST Colloquium. And it's of course really great to have you here from northern Germany and from the UK. I think you're right now in Hamburg, as it seems. Yeah. So it is great to have you here. So Andrea, he one of the world experts in actually discovering, or he's the pioneer of discovering photo-induced phase transitions in a whole variety of different materials. He started off his career actually starting on working with the femtosecond lasers at his time when he did his PhD, for instance, at the University of Pavia. He then moved on as a postdoc, I think, to actually San Diego in California, continuing to work on ultrafast physics, X-ray spectroscopy, and X-ray pulses, and then went on to the Lawrence Berkeley National Lab, where he developed actually techniques to use actually sliced pulses of synchrotron radiation. And this led him then to his discovery of how one can actually engineer light-induced superconductivity, for instance, in striped cuprates or buckyball molecules, C60. And in 2004, I think he became then a member of the faculty of Oxford University. And just shortly after, in 2006, he was already promoted to a professor at Oxford. And then he became a founding member actually of what then became in 2000, I think in 2013, the Max Planck Institute for Structure and Dynamics of Matter. And he joined there as a director in this precursor institute in 2008. So since then, Andrea is now director at the Max Planck Institute and also professor at the University of Oxford. And he, as I said, works, for instance, on photo-induced transitions in various kinds of matters. Now also got interested very much in how to manipulate actually lattices in solids using Terahertz, Terahertz radiation. And then he also realized that it's really required to probe driven materials with novel probes, and helped really much in the development of the free electron laser and its application. For his work, he received a lot of different prizes and awards. For instance, the Max Born Medal, the Frank Isaacson Prize from the APS, the Danny Heinemann Prize, and many more. So today it's our great pleasure to have you here. We are looking very much forward to your talk, actually telling us about how we can actually reach novel phases of matter if we go far away from equilibrium. It is really great to have you here. And it's also great that you actually talk to so many of our students and PIs during these days, which is of course always great to get insight from different perspectives, also for our excellence cluster, from somebody who can tell us as much as you can. So we are looking forward to the talk.
Thank you very much for this kind introduction. Let's see. So I have prepared a talk which is nominally about the physics of quantum materials when they're being driven periodically by external stimulation, but they will be very much focused on the physics of non-equilibrium superconductors, and specifically of non-equilibrium superconductors in some organic materials. Nevertheless, I hope salient aspects of the physics will come out. I have decided not to give you too many examples and to just rather try to flesh out some of the key observations and some of the questions. So I'm going to start with basically a placeholder slide, or a generic slide that has to do with what most of, or a lot of, modern condensed matter physics is about, which is about tuning properties that usually are functional. That means that they can achieve a performance near equilibrium. So this is one takes a material, and there's a number of parameters that you can drive generally slowly or quasi-adiabatically. For example, change in temperature or pressures in the left-hand side, I show a phase diagram with the doping. The number of dope charges are changed in for example, in unconventional superconductor. And one exhibits different phases of a material, which very frequently are characterized by their properties, both at very low frequencies and DC and at finite frequencies. Here, there's the example of superconductivity, which is ultimately characterized by their DC electrical properties, that is, the resistance, the DC resistance vanishes below a critical temperature, and the perfect diamagnetism, which means that a magnetic field is expelled. Again, a DC magnetic field is expelled below the transition temperature. And optimization of this and other phenomena in solids is generally done in sort of by driving the material adiabatically. I think I mentioned this already. The crucial aspect of the physics that we're interested in rely on the idea that a classical but also a quantum system, when it's being driven periodically or away from equilibrium, not only exhibits quantitatively different phenomena, but sometimes qualitatively different phenomena. So the idea is to have, for example, a high frequency dynamical modulation, which is applied on a material, and then create, on average, a different energy landscape that can generate qualitatively new functionalities. As I mentioned, this is well known in classical systems, ranging from spinning saddles and ion traps and Kapitsa pendulum. There's many situations in which driving gives rise to new energy structures and hence new properties. But this is particularly interesting to us in the context of quantum materials. So we will think about a material in which a light pulse modulates the Hamiltonian in time, and we will ask, what are the low energy effective properties that average out these fluctuations, the drive that are sampled at frequency slow compared to the periodic drive, and how can I think about this? So there's a plot there, there's a sort of a drawing there that is a caricature of a cuprate superconductor in which a specific phonon, in this case, the phonon that modulates the distance between a certain oxygen atom and the superconducting planes, is being modulated in time to large amplitudes. So the problem will be one in which the equilibrium order parameter, energy dependent, order parameter dependent energy is now being perturbed and results in a change in the underlying structure, which then evolves in time on a time scale that can be either slow or fast, depending on the details of the system, but where, let's say, in the red free energy that I showed there as a second plot going from left to right, one may create, for example, a new minimum of potential where new physics is being seen. So in the specific context of superconductivity, as I mentioned, we do this in many systems ranging from ferroelectrics to magnets and other materials, but in the specific context of superconductors, we've explored this non-equilibrium physics in a number of materials, starting from the cuprates. Again, on the left-hand side, I am showing you a classical example that we started from. This is not what I will be talking about today, but by way of introduction, it's useful to connect to these experiments. In the left-hand side, I'll show you an experiment in which a competing order that suppresses superconductivity is being selectively melted with light, thereby allowing the system to reach its mean field superconducting transition temperature. This is an example which is not intellectually particularly challenging, yet technically difficult to do, in which we showed that if you melted the stripe order that suppresses superconductivity, we could induce a quasi-metastable superconducting state at temperatures far above the thermodynamic transition temperature. And more recently, in other systems such as YBCO, we showed that by modulating certain atoms, we could induce coherencies, in fact, that look like superconducting coherencies, in fact, up to temperatures that exceed room temperature, and in fact, throughout this mysterious pseudo gap region that is found in the underdoped side of the cuprates. Again, this is not what I will talk about today. Today, I will focus on the control of superconductivity in organic conductors. Most of my talk, and depending on how slow I speak, probably all of my talk, will be about driven alkali-doped fullerenes. So this is the case of the potassium-doped or other alkali atom-doped fullerenes, which are high-temperature organic superconductors, and in which we will study how the excitation of certain molecular vibrations can affect the superconductivity away from equilibrium. And I will touch on to more recent experiments in which we've started studying another different class of tunable superconductors, which are these charge transfer salts, which again are another class of unconventional superconductors with interesting order parameters that we've recently shown can be made high temperature superconductors by optical driving. So the work that I'll discuss has been primarily done by three people. The first person is Matteo Mitrano, who was my student who discovered this effect in potassium 3C60. He is now graduated a few years ago. He has joined the Harvard faculty this year, continuing on these topics. Alice Cantaluppi was a student with me that followed Matteo, continued working on C60. She worked on the same, I will discuss this, she worked on the response on these systems by applying hydrostatic pressure, so that will be part of what I tell you. And then Matthias Budden, who just graduated, who worked at lengthening the lifetime of these states. There's also work at the end by Michele Buzzi and by a number of scientists in my department, including Gregor Iotsu, who I'll mention later, Thomas Gebert, Daniela Nicoletti, Erin Wang, and Guido Meyer, all very substantially important for all these experiments. So alkali-doped fullerenes. The way we should think about alkali-doped fullerenes in its most, let's say, romantic view and sort of stripped down view is that of an FCC lattice of C60 molecules, which are electron doped 3 times by 3 alkali atoms. Okay, so basically think about an FCC lattice of C63 minus molecules in which the lowest unoccupied molecular orbital is now being filled by 3 electrons. And this material becomes superconducting in the potassium case, becomes superconducting at approximately 19 Kelvin. There's cesium and rubidium become superconducting at higher temperatures. But this is the material that we study. And superconductivity is manifested by, as I mentioned before, by a number of DC properties, including the DC resistance, which, as I said, goes to exactly 0 below 19 Kelvin. These are samples that now we've learned how to grow ourselves in an MBE, and we now do experiments with thin films of C60 that are grown by and developed by my postdoc Erin Wang. So there's other features that reflect the superconducting state, not in the DC properties, but in the AC response at low frequencies. And these can be seen by basically by looking at the optical properties and energy scales, say at frequency scales, which are somewhere around terahertz frequency. So just for your reference, 1 terahertz is about 4 millieV, or about 50 Kelvin. So here we can measure the reflection or the complex reflection in optical conductivities, say at frequencies between 500 gigahertz and say approximately 7 or 8 terahertz. And if you do this, what you find is that the reflective exhibit at equilibrium some very clear features that are considered one-to-one corresponding to the superconducting state. And these features, I'm going to belabor this a little bit because they will be important as I walk you through the response of the material in the time domain. So if you take a superconductor like C60 at temperatures higher than the superconducting transition temperature, that is in a metallic state, what one finds are optical properties that are reminiscent of a metal. So what one has is a reflectivity edge at a certain frequency that depends on the density of free carriers, a real part of the conductivity that is a DC, a finite number, and then rolls off at a frequency that is approximately the scattering rate. And then an imaginary part of the conductivity, so the out of phase response of the current when I apply an AC electric field, which is peaked at the scattering rate. So this is basically the Drude response of a metal, which when becomes superconductor, it changes drastically. The first thing that happens is that the reflection coefficient becomes exactly 1 for all frequencies up to an energy scale, which is the superconducting gap. The real part of the optical conductivity is 0 for all frequencies below the gap, except at 0 frequency, which is not shown here, where I have a delta function in sigma 1. And this delta function is reflected in the imaginary part of the conductivity, which diverges like 1/omega toward low frequency. So the presence of a pole in the real part of the conductivity is reflected by a divergence toward low frequencies of the Kramers-Kronig transform of sigma 1. So the fact that I see this divergent sigma 2 is really reminiscent of or is indicative of a lot of spectral weight piled up at 0 frequency. So these are the features of a let's say an S-wave superconductor at the frequencies that are comparable to the superconducting gap. So this I've said, gap in sigma 1 and divergent sigma 2. What's interesting about this material is that although it's a strongly correlated superconductor, there is some degree of agreement on the microscopic physics that leads to pairing and superconductivity, which is related to the physics of each one of the molecular sites. Remember, each one of these sites occupies one of the FCC sites of the lattice. And if I take the undoped, undistorted fullerenes, what I have is so before I add the potassium C60, what I have is 3 unoccupied, degenerate, lower unoccupied molecular orbitals. So these are LUMO states, which are degenerate. And so these are T1U orbitals, but basically they're P orbitals that are pointing in 3 directions along the crystallographic directions. And once I dope those to 0 order in an undistorted molecule, I expect these 3 electrons, because of Hund's rule, to occupy these orbitals in a high spin state, except that the material, the molecule in this way is unstable against the Jahn-Teller distortion. And so the molecule sort of distorts and creates a low spin state, which is an S1/2 state. And this is, of course, validated, for example, by NMR and by all sorts of measurements. This is a low spin state in which the singlet here occupies, basically fluctuates between each one of these 3 orbitals, and it is assisted by molecular distortions. And it is believed that the orbital fluctuations that delocalize the singlet state around these 3 orbitals are the ones that ensure that this low spin state also generates a condensate and a superconductor. So this is by and large the modern theory of superconductivity in these compounds. There's basically this negative Hund's rule, which is a combination of that favors a low spin state, which is a combination of a Jahn-Teller distortion and in electronic interactions, which then mediates superconductivity. It's basically a molecular version of RVB in which fluctuations around the molecule give rise to a superconducting state. So when we started working on this, what Matteo, who was starting the PhD with me, said, well, basically, perhaps, just perhaps, if we can take a light pulse and stimulate these vibrations, we might be able to assist these fluctuations and control in either one of the 2 directions the superconducting state. Maybe we can make it worse, or maybe we can make it better, and try to understand how these fluctuations happen. And so the idea was now to take a mid-infrared pump pulse, which is resonant not with the Jahn-Teller distortion, but with another vibration that then couples to the Jahn-Teller distortion. This, would require too much detail for me, but something that is related to this pairing vibration. And so what Matteo thought was, maybe if I shake it right, and then I use a second pulse at high temperatures, and then I use a second pulse to interrogate and look for the opening of a superconducting gap, I might be able to see these features reproduced or reduced or changed in an interesting way. And so one of the most striking observations that was pretty clear early on is that at least, at a pretty good quantitative level, one could go to 100 Kelvin, which is 5 times the thermodynamic transition temperature, pump a specific vibrational mode, and induce optical properties starting from the red metallic features and induce these blue metallic features, so reflectivity of 1 and opening of a gap, that are very similar to the ones that I obtained below TC. In particular, the divergence of sigma 2 seems to be pretty similar to the divergence that I get at 0 temperature, indicative of a delta function induced at 0 frequency that is approximately of the same size as the one that occurs when the system condenses by its own devices. So some form of stimulated condensation that is, and secondly, an excitation gap that appears to be larger than the equilibrium gap. And whether this is really a superconducting gap or the beginning of a polaronic peak is not 100% clear. But nevertheless, qualitatively, one can at least say that this is a superconducting-like optical spectrum, in as much as it has a gap and it has a very high conductivity, as shown by these features. The other very good thing, before I start raising all the questions and all the problems that these observations are causing, is that, as I mentioned before, you can plot now some sort of figure of merit. You can decide that the size of this gap is a figure of merit of the strength of my superconducting state or superconducting-like state. And then you can plot now this integral as a function of base temperature. Remember, equilibrium TC is approximately 20 Kelvin. And then you can convince yourself that there's a very good gap. In fact, a gap that is even larger than the one that I open at equilibrium, all the way to 100 plus Kelvin. And then I still have a finite gap all the way to 300 Kelvin and higher, except that somehow this gap is only a partial gap. And my degree of certainty when I say that these properties are superconducting-like as opposed to these properties decreases with the amount of blue that I've put it in this plot. So although there is an increasing mobility at all these frequencies, I would argue that the bluish states are the ones where the sort of the equivalency with the optical properties of the equilibrium superconductors can be established. So this is all great. So you have a high temperature state, which nevertheless only lives for a very short time. If I plot again the integral of sigma 1 as a function of time, which is a large number at negative time delays when the material is a metal, and it goes basically to close to 0 after the material is being excited, this state, I find a state that lives only for a very short time. When I stop pumping it, it disappears, indicative of a state that doesn't have intrinsic rigidity. Basically, it only works by virtue of the fact that somehow rigidity is being supplied from outside by the drive. Okay, we could sort of belabor this a little more later. But this creates all sorts of trouble, and also the fact that transient superconductivity, you can see that I've been conditioned by a lot of conversations with the referees. Transient superconductivity is a very slippery concept because whilst at equilibrium, I can think of a superconducting state in which all the spectral weight, say sigma 1 in this metallic state, is squashed to 0 frequency in this delta function, which then is reflected by divergence in sigma 2. The moment I make the lifetime of this state shorter and shorter, what will happen is that this delta function will basically broaden up to a frequency, which is basically the inverse lifetime. And for a lifetime, that is, you see, some sizable fraction of the gap, what I'm left with is something that is a high mobility metal which is effectively a scattering rate, which is the lifetime of the state. And so at some level, one wouldn't go as far as saying that this is sort of a pseudo assignment, but one needs to be very careful when one characterizes these features and only looking at frequency scales that are significantly larger than the inverse lifetime of the state, so that one is really talking about quasi-static features, not quasi-static in the sense that the system is not thermalized. This would be at least a subtle issue, but just in the way the measurement is made, I can only trust data at frequencies higher than the inverse lifetime. I mean, this is somewhat an obvious statement. So the next step that we have entertained, that this took a long time, but what we started a long time ago was to try to increase the lifetime of the transient state. Firstly, to get rid of this problem of the sort of lifetime broadening. And secondly, also to be able to do other measurements, which we're now attempting, such as conductivity, magnetic field expulsion, and all the things that are done near equilibrium. So this is work that was led by Matthias, who graduated just now, and Thomas Gebert, who's a staff scientist in our department. So the idea is basically the following. If I can take a pulse and instead of making it 100 femtoseconds, I can make it a nanosecond. And if I'm lucky enough that I don't evaporate the whole material because the total energy of this pulse can be kept low enough, maybe I'll be able to stabilize this state for long enough that I can measure with other means, and also look at rigidity of the system at long times. So what we need is a mid-infrared pulse that has a lot of power, around 10 microns, turns out, and that can be used for these pulses. And of course, everybody who is taking a laser physics course knows that you look into the technology of the 1970s. There's of course CO2 lasers that you could buy at the drugstore on the corner, which generates kilowatts of radiation, which is used to drill holes in laminates, and is a very sort of efficient way in this to generate 10 micron radiation. One of the problems, if you want to do sophisticated experiments to drive the superconducting state, is that the high power versions of these lasers basically have a lot of longitudinal modes that beat with one another and give rise to a very not well-behaved pulse structure if you don't do something special. What Matthias and Thomas did was they basically took titanium sapphire femtosecond technology, which sort of operates at 1.5 EV radiation, or 800 nanometers, 0.8. So let's talk about in wavelengths here. 0.8 micron radiation. You can use some nonlinear optical techniques to generate 10.6 microns, see the CO2 laser, which then of course would make those short pulses long because of the finesse of the cavity, and then generate a train of pulses, which is well behaved and most importantly is absolutely synchronized to an external femtosecond laser. That turned out to be a little harder than what we thought. You could now use a Pockels cell to separate these pulses out. Turned out that you had to re-amplify it, and we could have these nanosecond pulses at 10 microns, which then we want to now slice into pulses that could be made either very short or long. And so, as a good way about this, we use the femtosecond pulse and use the semiconductor mirrors to basically slice the front and the back. These semiconductor mirrors that were could be excited by visible pulses at controllable time delays between these two pulses. And so we could slide one in reflection, one in transmission. So the excitation of the semiconductor makes a semiconductor which is usually transparent, opaque. And so what I can do is I can slice the front and the back of this pulse, again, in a way that is absolutely synchronized to an external femtosecond laser with very nice, controllable, sharp. This is a little harder than what it looks like, but conceptually it's straightforward. And so what we could do, again, is develop a new laser source that could drive the system using pulses that could be tuned between a couple of picoseconds and a nanosecond. and which could be then coupled with conventional Terahertz technology, so that we could again use the same mid-infrared techniques, Terahertz techniques, to go search for these superconducting gaps in the spectral regions where Matteo saw the short-lived opening of the putatively superconducting state. So this is, again, is conceptually straightforward, but technically not so. And Matthias worked very hard at developing this source. And so he could do experiments in which now, instead of having 100 femtosecond pulse, he could drive this with a pulse that was 3,000 times longer or 10,000 times longer, up to a nanosecond. And again, at 100 Kelvin, so 5 times above equilibrium TC, lo and behold, what he discovered was that already 100 picoseconds after the drive pulse was terminated, he could still obtain optical properties that were compatible with the appearance of a long-lived superconducting state, which no longer disappears in 1 picosecond, but lives all the way to 1 nanosecond. Actually, 12 nanosecond is the lifetime that we find. If you are thinking that our data is noisy, you should think that this experiment is now done at 13 hertz as opposed to a kilohertz. So the noise of the measurement is a little bit, but it was sufficient to convince ourselves that the response was superconducting-like all the way to at least 1 nanosecond. And again, this is sort of an equivalent observation to the one that we observed, that we reported in the previous paper. Again, this is the same measurement. You see the reflection coefficient that goes to 1 and then lifts up to 12 nanoseconds. And the gap that opens up during the pump pulse and then continues on all the way to many tens of nanoseconds. So this is suggestive. Well, firstly, it takes care of the problem of the lifetime broadening of these features, and makes, of course, the observation of the optical properties much more reliable, because now this delta function that I see here is going to be 10,000 times sharper, and in fact comparable to the width of delta functions that are being observed in, at least in the semiconductors with junk at the surface. Okay. The second thing that I can say is that what one can do is now start thinking whether one can do the same experiment by directly measuring electrical transport and observing a zero resistance state as a precursor to maybe doing more sophisticated measurements that involve magnetic responses, maybe even tunneling, and other features that are proper of equilibrium superconductors. So just to look at what we can expect, what we can take is these data that I have shown you, and I can apply a Drude model. I can just say, I run an unbiased fit, whether this is a superconductor or not. I can extract the zero frequency conductivity from the Drude-Lorentz model. Basically, this is a signature of the superfluid density or of the carrier density. And I can predict that the extracted sigma zero, the extracted rho zero, which is the inverse of sigma zero, goes from 1 milliohm per centimeter to something that is compatible with zero. And that lives for about 1 nanosecond. Again, I'm repeating things that I've shown you already. But what these optical data show is that if I could measure the DC resistant with leads, I should see a conductivity that drops at least 4 orders of magnitude. Now, the error bars here, so my ability to check zero resistance, is connected to the lowest frequency at which I'm measuring here. Of course, the conductivity cannot be assessed to be 0 if I'm only measuring down to 1 terahertz. Okay, but this is a pretty promising observation. I expect this thing to be in the micro-ohm per centimeter range. And so what Matthias and Thomas did was to sort of do the same experiment, but rather than using terahertz, doing electrical transport experiments. Turns out that with these powders is not so straightforward. So there's a whole set of technical aspects that are required here to do these measurements. Again, help with a lot of help by Guido Meyer and Toru Matsuyama. We were able to do fast measurements, first with 2 probes and 4 probes, although the 2 probe measurements appear to be more reliable at this stage, and basically observe directly a light-induced effect in which the resistance went to a level that is compatible with 0, and again living for a time that is, tens of nanoseconds. So here the relaxation seems to be slightly different than the one we extract with optics, 30 rather than 12, but by and large this is good enough for an experiment at this level of sophistication. So what's very interesting, which is an effect that we did not predict, was that if you plot this resistance as a function of fluence, what you can do is you can basically change either the pulse duration and reduce the intensity and maintain the area, or keep the duration short and increase the intensity. But be as it may, what we find is that the light-induced state is only dependent on the total energy inside this pulse. So basically the area of the pulse determines your ability to turn the state into a zero resistance state. And because I want to tell you a few other things, I will not discuss what we believe is the reason for the long lifetime. But basically, I will only say that what we think is that I can imagine a state in which when I create this superheated superconductor and then I stop pumping it, this superconductor relaxes not by charge excitations across the gap, which is probably more rigid, but rather by fluctuations of the order parameter phase, which then sort of diffuses and nucleates phase slips. And actually a calculation by our colleague Dieter Jaksch, who has been actually helping us trying to understand just on the basis of a time-dependent Landau-Ginzburg formalism, we have been able to fit the relaxation time of the optical of this zero resistance state by simply considering what the phase diffusion would be in a superconductor with the microscopic, in a superheated, highly superheated superconductor with the microscopic parameters of potassium C60. So this brings me to the last part of the talk here, which has to do with finding ways to A, tune these properties of the light-induced superconductor, and B, try to understand, it's a step toward understanding whether the features of this light-induced long-lived zero resistance state has other characteristics of the superconducting state. So one of the important points that I will discuss here is how if you either change the alkali atom or you apply pressure, as you reduce the lattice constant, so if you apply pressure, the superconducting transition temperature on at least the lattice constant that are smaller than the dome, than the peak of the dome, tends to reduce. Okay, so this is especially for potassium C60, which sits around here, 20 Kelvin. This is clearly applying pressure gives rise to a reduction in TC. So the reason for this is, at least in the context of very basic ideas of a BCS superconductor, is that by applying pressure, the hopping amplitude becomes larger. So in a sense, the effective mass becomes smaller, and this reduces the density of states at the Fermi level, which by very simple concepts derived, for example, by the Macmillan formula, tell you that a superconductor will tend to become worse with pressure. Basically, the reason for this is that superconductivity doesn't like fast electrons. What you want are really slow electrons which can then are susceptible to pairing, because basically the nesting is favored. On the other hand, if the zero resistance state is one, or this high mobility state is one which has to do with a metallic state, maybe an unconventional, perfect conducting state, what I would expect is the opposite effect with pressure, with external pressure. And the reason for this is that sigma dc in a metal basically scales with the effective mass and the carrier density, which are both quantities that become more favorable as I apply pressure. In other words, they depend on the sigma dc depends on the square of the plasma frequency, which shifts to the blue as I apply pressure or as I reduce the effective mass. And so in a sense, what I can do is redo this experiment under pressure and now look at the light-induced state and then apply pressure and look at this zero resistance state and ask the question, is this getting better or is this getting worse with pressure? Because if it's getting better, then maybe it's more of a metal. And if it's getting worse, maybe this at least goes in the direction of another more complicated state. So this is Alicia's PhD thesis, who basically redid all these experiments by figuring out how to do them in a diamond anvil cell, which is, again, required quite a bit of just rediscovering things that professionals know how to do, that we had to learn from scratch. So I won't tell you this, and I won't tell you this, but I will tell you that when Alicia does the same experiment that Matteo did in an unbiased diamond anvil at 0 gigapascal, she found, after some work, exactly the same results that Matteo found. That is opening of a gap and divergence in sigma 2, okay? And now she redid the experiment starting applying pressure, and you should watch the divergence sigma 2 in the opening of the gap as the base pressure is walked from 0 gigapascal all the way to several gigapascal. So as you can see already at 200 megapascal, the gap fills in and sigma 2 is not as exciting as it used to be. You know, at each one of these pressures, we calibrated the metallic state independently. Already at half a gigapascal, you can see the gap basically gone and sigma 2 starting peaking, indicative of a scattering rate that is walking in from being very low to being much larger, and a gap. So this light-induced state gets worse with pressure, consistent with an equilibrium superconductor and rather than a metal, okay? So now I can use this effect. If I fit this data as a function of pressure and temperature, I can use these tuning parameters to try to create at least a proxy for a phase diagram for this non-equilibrium state. So this is what Alicia did in great detail. So what she did was she took these optical properties, again, as I did before when I was discussing the zero frequency conductivity in the context of the long-lived state. What you can do is you take the sigma 2, you check how divergent it is, and then applying the Drude-Lorentz fit, you can extract the sigma 0. So the real part of the resistive conductivity, which should be infinity, which is the inverse of the resistivity as a function of pressure. So firstly, let's start at high temperatures in the metallic state before I pump the system. And now at 3 temperatures, 100 Kelvin, 200 Kelvin, and 300 Kelvin, if you take now sigma 0, which is the extrapolation of the sigma of omega calculated, measured here in the metal, what you find is what I had promised you we were going to find, that is a metal, the conductivity of which gets better as I apply pressure. So in equilibrium, the metal behaves like a metal, that is conductivity gets better. But if now go in the light-induced state, at low pressure, you can see sigma 0 is basically infinity plus or minus 10 to the 10. So it's some number that diverges, and it can be only assessed to a degree of precision that depends on the lowest frequency cutoff of my measurement. So my ability to extrapolate to zero frequency depending on how low frequency I can measure. But you know, at low pressures, I can tell that at 100 Kelvin, sigma 0 is basically infinity, whereas sigma 1, so rho 0 is basically 0. And then as I apply pressure, what I find is that unlike in the equilibrium metallic state, for a certain interval of pressure, sigma 0 reduces. This is related to the gap closing until you get to about 1 gigapascal, where sigma 0 starts growing again, indicative of metallic response. So the photoexcited material at 2.5 gigapascal, although is a state with higher conductivity, is also a state in which conductivity goes up with pressure. And you can now sort of, do this as a bunch of temperatures and magnetic fields and pressures, and you can plot this, and then once you put in a color plot and you smooth the data, it looks much more impressive. So you have this very small sliver of behavior here in the low bandwidth, in the highly correlated side close to the dome, where the response is superconducting like, that is to say, where the light-induced conductivity gets worse with pressure in the same, so the slope, in the same way that this happens at equilibrium. Whereas here, which, at first sight, maybe if we had known this 5 years ago, we'd have written a paper saying that this yellow side was also light-induced superconducting like state. We find something that is more, that perhaps is not really so superconducting, but it looks like more like a high mobility metal as defined by a figure of merit that I've arbitrarily decided is enough for now, that is delta sigma 0 and delta p bigger than 0, okay? But this is taking us to a place where we can now sort of make statements where we say that, the material should be strongly correlated and possibly fluctuating, and I will get to that in a second, if I want the system to be superconducting. So how much time should I wrap this up?
I think we have about 10 more minutes.
How long?
So it's about 10 more minutes, but that is on, with a couple of questions afterwards.
I just want to make one point. I will try, I have too many slides, but I will just try to say two things. And I'm happy to take questions in more detail. I'll just give you the qualitative points.
Cool, sounds great.
So the argument here is because this effect appears to happen in the cuprates and in the fullerenes only in these regions close to, remember the phase diagram has a dome here and a mud insulator here, only when, and we haven't been able to measure on this side, but only where the correlations are large enough, is light-induced superconductivity some form of manipulation of fluctuations of the normal state. And this is actually informed by other studies that we've been making a lot of progress on in the cuprates, collaborating closely with Eugene Demner's group at Harvard, where we've been sort of making a number of sort of critical assessments on the nature of the cuprate light-induced state. But the question is, light-induced superconductivity some form of manipulation of an already fluctuating superconducting-like state, however you want to call that, superconducting state in the normal state above TC. And so to do this, what we did was, so this is the work by Gregor Yotsu, who's actually one of the people that has moved from optical lattices. He worked at the ETH with Tilman Esslinger before joining us as a postdoc, and two colleagues from Oxford, Arjun Ardavan and Munson Nam, where we tried to find ways to diagnose the nature of the fluctuating state in the normal state of the cuprate. So we resurrected at equilibrium measurements of the Nernst effect. Basically, the Nernst effect is a measurement of a transverse voltage for an applied magnetic field in the perpendicular direction in presence of a thermal gradient. So this is an effect that happens when the material is close to TC, where I have vortices, where vortices diffuse and therefore create a transverse voltage. But as famously being, so this is another caricature of these vortices drifting in presence of a gradient, and thereby generating, as they cross here, because of basically a Lorentz force, they generate a transverse voltage. And so there's been famously very interesting experiments done by Foy-Nong's group at Princeton, who showed that in the cuprates, you have a very large Nernst effect in very important regions of the phase diagram of the cuprates. And this, although this is a highly controversial and discussed topic, it has been taken as an indicative of the presence of pre-existing superconducting fluctuations above TC. And again, the first qualitative point that I should show you, as after a lot of work, what Gregor showed is that in the C60, which by the way is a three-dimensional system in which a superconducting Nernst effect was never characterized, this is unpublished data. What Gregor showed is that you have a very sizable Nernst effect at temperatures that are far in excess of TC, And depending on how you fit the negative quasi-particle contribution, it could be all the way up to 100 Kelvin, but certainly up to 50 or 60 Kelvin. And so the first statement that I want to make is that we seem to be seeing, if you want to draw conclusions, we seem to be seeing this light-induced effect in systems that exhibit a high temperature Nernst effect. That is the cuprates and some of the buckyballs. And so what we did from that, we said, well, maybe then any system that has a Nernst effect, if it's excited right, should also give rise to this light-induced transient effect. And what I will show you here, here's the question: materials with a normal state Nernst effect, could it be said that they exhibit optically enhanced superconductivity? And so, and this is the latest work that is led by Michele Buzzi, where he took this specific kappa ET2 compounds. This is a well-known family of charge transfer salt, again, which are a placeholder, sort of been studied in great detail as unconventional superconductors in which correlations are important, and in which a superconducting state is close to an antiferromagnetic mod insulator, and with some regions that in the right bias also exhibit some important spin liquid physics. And most importantly, materials that in some regions here close to the Mott insulator exhibit a very large Nernst effect, as discussed by Moonsan and Arjun in this Nature paper about 15 years ago. And so what Michele did was to take these compounds and excite them in ways similar to what I'm doing with what I was doing with the buckyballs. And lo and behold, what he discovered was even a clearer, in terms of quantitative details and some rules transfer and everything, is in a clear demonstration of a transformation between a metallic set of properties at various temperatures and a light-induced superconducting light state, in which basically all the spectral weight from the metal is being transferred to a pole at zero frequency. So respecting of the in a non-equilibrium version of the sum rules. So that's basically what I wanted to tell you. And if you take the version of the material that has the Nernst effect, we see this light-induced state, whereas the versions of the material that do not have the Nernst effect do not show this light-induced state. So at the moment, we are pursuing this qualitative intuition that light-induced superconductivity is some form of manipulation of a fluctuating state at high temperature that has some features of the superconducting state. And also what I discussed before about the lifetime of the light-induced C60, light-induced state of C60 as being determined by the nucleation of phase slips and vortices, or as a phase randomization type of relaxation, is perhaps, let's say, coherent or in line with these ideas. Okay. Right, there you go. I already said this. Where there's a Nernst effect, there's a light-induced state. This is where the Nernst effect is observed in these compounds. Here we find no light-induced state. Here we find no light-induced state. And here we find a light-induced state. At least qualitatively, we seem to be able to find. So outlook. So this is, again, work led by Gregor, who has started. He came up with this conjecture where the next step is really to probe whether a magnetic field is being expelled in these systems. And of course, what you need to find is you need to find a way to be able to measure a magnetic field at the surface of this material in the equilibrium, both in the metal and in the superconducting state, and also in the light-induced state. And so what Gregor is working on together with my excellent student, Giovanni De Vecchi, who's leading this, and Michele Buzzi is also helping out with this, has been to put a magneto-optical material like a garnet slapped on top of the superconducting or non-superconducting state, and then have a magnetic field that threads this sandwich of the superconductor and the garnet, and then use a time delay pulse to try to to look at polarization rotation in the magneto-optical crystal, to have a quantitative local measurement microscopically of the magnetic fields I expect to be invited again if this experiment works. We already have some very interesting results in which we can destroy a superconducting state and we can observe a field that used to be expelled not being expelled anymore. Of course, the light-induced state, for a number of reasons, is harder to do, so I won't belabor this any longer. And also for this, we have measurements already. So this is Erin Wang, who has been able to show that the same transport measurements that we use to other on nanosecond timescale, but also at femtosecond timescale with other techniques that I have not had time to discuss here, we've been able to show critical current measurements in the light-induced state. So we can find already basically that if the current that is used to probe the sample becomes of order HC2, then I can generate something that looks like a depairing field, and I have a very clear nonlinear critical current response. This is again, but this is outlook. I suppose that we are now in sort of in a regime in which we have decided that we rather than trying to understand what the microscopics of this phenomenon is, we're just trying to gather as much hard evidence on all the properties of this system, because in a sense, whether I should think of this as some form, what form of condensation is one that is being stimulated by light, and should it at all expel a magnetic field? A Bose-Einstein condensate does not expel a magnetic field, as far as I know. If it's not gapped, so who knows what the results of these research are going to be. Okay, I think I talked too much. I'm not even going to say, okay, light-induced superconductivity, tunable lifetimes, nanosecond lifetimes, reveal zero resistance, phase diagrams for light-induced superconductivity. That's the summary of my talk. Thank you for your attention. I am happy to take any question you might have.
Thank you so much, Andrea, for this really excellent talk. We have some hands going up, but let me also do this a little bit acoustically. So thank you very much. Do we have questions? And maybe just raise your hand in your participant list, or just speak up. Maybe let me, in this case, actually ask a couple questions. So you actually answered one already in the end. What's the status of the magnetic fields? Because that also will tell us about probably if there's even is there classification of which type of superconductors that these actually are? They don't have to be type 1 or type 2.
I don't really know. In a sense, because in many of these systems, you're depositing energy over a thin layer. Actually, I don't know. But more importantly, is it type 1 or type 2? Is the system thermalized? Mm-hmm. These are sort of more fundamental questions that what are the magnetic properties of a stimulated superconductor, provided that we even understand what that means. Let's say that I have, let me put it like this. Let's say that I believe that I have preformed paths, and that the action of the periodic drive is simply to synchronize these preformed paths in some form of stimulated condensation. Okay. Then under those circumstances, I would imagine for this light-induced state to inherit whichever type of superconductor it was. And in all these unconventional superconductors, these would all be type 2 superconductors, of course. So these are ones in which the coherence length is pretty small. But then again, who knows? That's I don't know.
But maybe just to follow up, so is the picture maybe also that you have this valence bound type of states which build your bosons or the spin up and spin down bind?
Yeah.
And via your pulse, is it basically that the binding energy of this two-body state, this valence bound state, becomes stronger and thereby the gap increases?
It could be. Okay. Actually, that's something I said a little bit in passing. When we looked at the data, we say this gap is twice as big, for sure. On the other hand, if you look at the spectroscopic features of C60 itself, what you find is that there is a polaronic peak that starts raising. And so whether we're really seeing the gap or the gap is maybe much larger even, I don't know. But for example, let me actually show you these data. Okay, these are very nice. So this is now light induced in the kappa salts, and what you see is a gap which scales with temperature, by the way. It gets smaller and smaller up to the light induced TC, let's say, of 50 some Kelvin. In this case, the ground state doesn't even have a gap. So it looks like the symmetry of this light induced state may even be different than the one you have at equilibrium. This seems like really a textbook S-wave superconductor in which the Tinkham Ferrier rules are, it basically looks like mercury, in which all the spectral weight that comes from here goes into the. So I don't really know whether, but going back to C60, I am becoming convinced. I convinced myself that we are acting on the phase by stabilizing the phase, by enhancing the phase rigidity, by driving. But this is a complete speculation for which I have no evidence.
Do we have more questions?
I would have one. Richard, I would have.
Yeah, Ignacio. Oh, hey, Alex. Yeah.
Hi, Andrea. This is Alex Holleitner. Very nice talk. Nice results. I have a naive question. For instance, what you just showed for this transition, you always show sigma 1 and sigma 2, and basically you rely on the let's say, Lorentz response theory. Do you see it in the signal and also in the spectrum? Do you see differences when you fit the real data? I mean, when you fit the data, that the response theory has to be adjusted as well. I mean, you see the transitions, but does the...
Just 1 second, Alex.
Yeah.
What you just said, let me defend it. So what you said, sigma 1 and sigma 2 come out of the data just by measuring amplitude and phase. So small r, r1 plus I, r2. And there you extract sigma 1 and sigma 2 with no bias. When we extract sigma 0, there we fit it with a Drude-Lorentz fit, for lack of a better. But this is only every time we try to say, what do we expect the zero for the equivalent zero frequency conductivity to be? Sorry, keep going.
Okay, no, that's fine. Okay, but you don't see any change in the spectrum or the spectral shape of the response function or something?
I mean, the Drude-Lorentz fit, when we try to extract sigma 0, is only used for that purpose and at frequencies lower than the gap. Right, so we don't, there you basically, sigma 1 is 0 and sigma 2 diverges as 1 over omega. So in that sense, is by construction a perfect Drude-Lorentz fit at frequencies higher than the scattering rate. We have selectively chosen a spectral region where Drude-Lorentz works by construction. But this is only for the purposes of trying to predict sigma 0, just to have one quantity to be looked at. Yeah.
Okay, thank you.
Yes, we have a question from Lad.
Hi, just out of curiosity, what do you think? What is the limit for how quickly you can make or can turn on this superconductivity?
Okay, so what do I think? So this is now a complete extrapolation from, let's imagine that you are basically dealing with a bosonic system in which pairs are basically, so the energy, let's say that the energy scale for the pairing is T star, some high, and so T mean field is infinity, and then in reality, in equilibrium, you have an order-disorder transition for the phase, which then you're synchronizing by some periodic drive. Then I would argue that the phase rigidity is the shortest time scale that you can sync those things up. And now let's take the opposite view. Let's go in a sort of an extreme BCS the world in which the phase is basically infinite energy scale, and now what you're doing is making pairs. Then I would say that 2 delta is the time scale, the faster time scale that you can form you know, in as much as the phase will respond much faster but this is, you know, not sure whether this is, you know, if you want to get slightly more sophisticated, if you believe that what you're doing is you're using a parametric drive to synchronize whatever degree of freedom you're syncing, then the speed at which this will happen will presumably depend on the area of the pulse that you're using in some, you know, well-known ways, even from classical systems. But a fundamental timescale can either be the phase rigidity. It can't get faster than the phase rigidity and 2 delta. I'm not sure this gives you a little bit of the parameter space where we should be thinking, I think. Yeah.
Thanks.
We have a question from Emmanuel.
Yeah, hi, Andrea, very nice talk. I'm wondering, can you probe the excited modes above this transient superconducting state to learn more about its nature? So do a double modulation in a sense. So you have your modulation, which induces superconductivity. And then on top of that, you have a probe at even lower frequencies that probes the excited states.
So this is a very good question. So we're working hard at using a Raman probe. You know, one of the questions is, what's the temperature of the state? So you can do 2 things. You can do optical photo emission if you want to do what the temperature of the electrons is, of the quasi-particles, and you can do Raman scattering if you want to know what the temperature of the modes, now getting back to your question, of the modes is, and you can look at Stokes anti-Stokes ratio. So we're trying to do that and see what the temperature of the modes are. But I wonder whether that's what you were asking.
You're muted still. Oh, yeah.
So I mean, I was thinking, are there things like amplitude modes or something also that you could measure?
So
in principle, if you do this kind of bond modulation, you should be able to see that should couple to those modes as well. I
mean, amplitude modes are difficult to see unless, I mean, I suppose one could do a pump experiment, because of course the amplitude mode, unless it's coupled to a CDW, is difficult to see in Raman, and it can be seen if it's driven nonlinearly. But you know, why not? So we have actually done experiments in which we saw that when you, in certain circumstances, if the quench is fast enough compared to 2 delta, what you get is an amplification. You get reflectivities higher than 1. And the way this was actually sort of something that there was a lot of famous theorists, including, you know, Eugene Ignacio is part of this, and various other people. Danny Podolsky is the guy that worked on this, and he explained this amplification by of the probe light as something that resulted from a possible coherent amplitude mode that was then parametrically coupling to phase fluctuations, phase-on fluctuations, and then to the probe field. But you know, this is a very elegant theory. What I can tell you is that whether it's true or not, I don't know. But what I can tell you is that, you know, there might be ways to look at it, but you have to go in nonlinear response. Sorry, I was rambling a little bit here, but I was trying to summarize it correctly. Yeah. So
I start to remember the talks from Eugene on this. Yes.
Yeah. Anyway, so Higgs modes are anyways, but you know, maybe one could see signatures of this if this Higgs mode is coupled to something else, then it becomes observable in some more conventional spectroscopies.
Thanks.
Do we have more questions? Maybe then let me ask you one last from my side. You showed how you expect in the Mexican head basically dephasing of your state, and if that happens, would then the quasi-particle picture at that point start to break down more and more in terms of actually the Bogoliubov excitations of the superconductor? I mean, you still have a gap, but how do you expand even your theory in terms of?
Yeah, the argument was semi-quantitative in the sense that what you find yourself in a state. So let me just first defend what the argument was, and then we can go back to your question. The point there was the following: you have a superheated superconductor, which is, you pump the system, you supply rigidity, presumably, you stop supplying rigidity, and now you have I don't know, ice at 300 Celsius, and so now this thing needs to decay, and you could say, well, it decays because it makes gap excitations, but that should go fast, picosecond or so. And so the argument was, okay, well, let's assume the gap is big. What's the most rigid thing that we can think of in this system? Then we said, okay, maybe it's the phase. And if you do a time-dependent Landau-Ginzburg effective theory, you could convince yourself that the phase will linger around. Phase rigidity, sort of, coherence will linger around because it's a bulk state for long enough. This was the extent of the argument. We never really had any ambition beyond that. So in that sense, I wouldn't know how to answer your question. I mean, it was never really a full theory. I mean, it was basically an effective low energy theory.
But maybe actually probing these low energy modes, which you mentioned, could help, because you could measure the occupation numbers also.
Of which modes? You mean the Higgs?
No, not the Higgs. Just really the Bogoliubov excitations out of the superconductor.
I see.
Because they
how does that work? I would have to do Raman.
Yeah.
And see the gap. Seeing the gap in Raman is pretty hard.
Okay.
Not even sure people have ever seen it in C60. I mean, you see well in the cuprates where the scattering cross section is infinity. So you see very clearly this B2G Raman peak in the cuprates. I think in C60, but again, C60 is a strange material that people stopped studying after the lab scandal. So maybe with modern techniques, one could, maybe this is possible.
Okay, thanks. So if you don't have any more questions, let's thank Andrea again for his really beautiful talk. That was very inspiring. So thank you very much.
Thanks, everybody. So I have,
and you will have still a continuous